Okay, hi y'all. So in this particular example, I do want to go ahead and integrate over a general region and kind of illustrate this example. So kind of to elaborate on rectangular regions, for a general region, if you want to take the area of a region, then all you need to do is you need to integrate over just the integral of a constant. Again, to take the area of the region by double integrals, you can do that by taking the double integral of just the constant r. To illustrate this, we could have done that with the last example in 16.1 if we wanted to. I will go ahead and elaborate that now. So recall from yesterday's class that for the area of the region, because it was rectangular, we were able to get that area was 4. If I were to use that formula now, I will also get 4. So let's illustrate that now. Here my region is from 0 to 2 for x and 0 to 2 for y. So to elaborate that formula in terms of yesterday's example, I would do the double integral from 0 to 2, and then from 0 to 2 of either dx dy or dy dx. If I were to do that, that double integral will be now 0 to 2, because I'm integrating with respect to y first. This will be y equals 0, y equals 2 dx. Integrating that will be integral from 0 to 2. If I plug in 2 for y, I get a 2, minus if I plug in 0 for y, I get 0. So I now get 2 dx, which that becomes 2x. If I were to take the antiderivative, going from 0 to 2, if I plug in 2, I get 4, minus if I plug in 0, I get 0. So if I were to use my area of a region equation on this example from 16.1, I will still get the exact same result that we got, which was that the area of the region is 4. So that means that that formula that we now have holds period, regardless if I'm working with a rectangular region or a general region for that. But with that said, let's go ahead and illustrate how we can find the area of a region with the following example. So let's say that we are trying to find the area of the region bounded by the following curves where x is non-negative. So before we continue, let's go ahead and get a sketch of what that region will look like. So I have the line 6 minus x, which I will use pink for. I'll go ahead and mark 2 points of interest. First, my y-intercept, which in this case is 0 to 6, and my s-intercept, which in this case is also 6, if I need it. Next is the line 6 plus 5x. Go ahead and graph that. Note that it also has the same y-intercept at 6. So 6 plus 5x. And y equals 6 minus x. And now I graph the third curve that we have, which is the x squared. So I'll go ahead and graph that in teal. And so with this, my region R is here. And my goal for this example is I want to get the area of my region. And the reason why is that's going to help me when we set up my regions for that. So to start that, I'll start with the lower green point here. I want to find that intercept. And because that is where x squared and 6 minus x are intersecting, I will find that point by setting those two curves equal to each other. So I will first set x squared equal to the 6 minus x. Now solving for x, I will get the following. First, I'll move the 6 minus x to the left-hand side. That'll give me x squared plus x minus 6 equals 0. 1 times negative 6, I can rewrite that as positive 3 minus 2, because 3 minus 2 gives me a 1, which is my coefficient in the middle. Multiplied together, that gives me 6. So my quadratic can be factored to an x plus 3 and an x minus 2 equal to 0. So from this, I'm going to have two solutions to that. It'll be at x equals negative 3 and x equals positive 2. However, I can go ahead and eliminate the solution of x equals negative 3. The reason why I can go ahead and get rid of that is because I'm told already from the problem that x is non-negative. Because of that, I cannot have a negative solution or a negative intercept for x. So I have to delete my solution of x equals negative 3 and keep x equals 2. So that point below, x value of 2, if I plug that into either x squared or 6 minus x, I will get corresponding y value of 4. Now, I'm going to repeat that same process for x squared and 6 plus 5x. So set those two curves equal to each other. Moving into one side, I'm going to factor is 2, x squared minus 5x minus 6 equals 0. Okay. And yes, I can get that. This can be factored. X equals -1 scenario and get x equals 6. And if you plug this into either the corresponding y value of 36. Now that we have our region and our intercept set up, let's go ahead and figure out what this region R is. The one thing that I want to emphasize here is I'm going to have y go from curve to curve while x is going from point to point. The reason why I want to do that instead of the other direction is because I am already given 3 different curves and they're already written in the form of x being that and y being the following. Okay, so keep on going from that. Note that when I set my region, note that I will have 2 separate regions for that. And the reason why, if y is going from curve to curve, then I'm going to have 2 different curves for that. particular, I have a split here. At x equals 2, my two curves split between having from 0 to 2 being the curves cis plus 5x and cis minus x. Whereas from 2 to cis, talking with respect to x, it will be cis plus 5x and x squared. So because a different order of my regions is occurring, my entire region R can be split into two different subregions. So because that is occurring, when that occurs, I'm going to denote that region R as a union of two different subregions. And so let's do that first for both R1 and then for R2. Okay, for R1, what I have is from x, that will be going from point to point. My smallest x value in that region is 0, and my largest x value is 2. Because of that, in the first subregion of R1, that is going from 0 to 2. Now for Y, where I'm going from curve to curve, my smallest curve is the cis minus x, and my larger curve is the cis plus 5x. So because of that, Y is going between cis minus x and cis plus 5x. And now we repeat the same process for R2. Again, because we want Y to go from curve to curve, because we already have them written in terms of f of x equals y, x is still going from point to point. And in R of 2, the smallest x value that I have is 2, where the largest s value that I have is that sits coming from that intercept. So because of that, in region 2, x is going from point to point, 2 to sits. Again, now for y, going from curve to curve, in R of 2, my smallest curve is the x squared, and my largest curve is the cis plus 5x. So in R of 2, this will now go from x squared, y, cis plus 5x. Okay. Now, if you have a region split into two subregions, the way that you will do that is the following. So my integral of the region of d of a, because I split this into two separate regions, this will be taking the area of R1 and taking the area of R2. And now I do both of those separately. Rewriting R1, x is going from 0 to 2, y is going from cis minus x to cis plus 5x of dy dx. X is going from 2 to 6, y is going from x squared to cis plus 5x. And now I integrate both of those separately. If I integrate same for the second integral. Okay. And now what I'm left with is first integral, that's from 0 to 2. Here you have 6 plus 5x minus 6 minus x. Simplifying that, you should be left with a 6x. Going from 2 to 6 of that, upper bound is the 6 plus 5x, lower bound is the x squared. So you should have 6 plus 5x minus x squared dx. And now we will integrate. So that will be a 3x squared. And that will be a 6x. It's 5 halves x squared minus a x cubed over 3. And if you do the evaluation here, you should be left with 140 over 3 after simplification. All right. Thank you all for watching. If you want to see a more detailed version of this solution, it will be posted on Canvas under the annotated notes page. All right.